invariants of links. Before I get there, and I'm going to be talking about SL2C holonomy invariants of links. Before I get to that, I'd like to thank Martin and Allison again for organizing the nearly carbon-neutral geometric topology conference. And I'd like to thank Carmen and Christine for organizing this session on quantum invariants and inviting me to speak. Again, I'd like to say, like in the first part, much of the math I'm going to be talking about is due to Kashai of Reshetikhin or Blanchet, Geer, Patureau-Mirand, and Reshetikhin, among other authors. I will be discussing some of my work building on theirs towards the end. Okay, here's an intro. In the previous part of these paired presentations, I gave the general idea and motivation for what a holonomy invariant of a link is. Again, the idea is it's like a quantum invariant, and you don't just have a link or some other topological thing. You have a representation of its knot group into G. Part two, this part, I'm going to talk about more details of a specific example. Due to Blanchet, Geer, Patureau-Mirand, and Reshetikhin, I'm going to call it the BGPR invariant. Maybe there's a better name that we'll come up with someday. I'm also going to discuss my recent work, which interprets their invariant in terms of the SL2C twisted Reidemeister torsion. The plan is that first I'm just going to discuss some properties of it, sort of what is this invariant and how does it relate to other things. And after we get through that, I'll talk about some of the more technical aspects of the construction, how you actually get this thing. Okay, so what is it? So here's the data you need for the BGPR invariant. Take link, L a link in S3, and R a representation from the fundamental group of the complement to SL2C. Pick an integer R greater than or equal to 2. So they come in a family. The simplest one is R equals 2. They get more complicated as this gets bigger. And pick some rth roots. So for each component of the link, choose a meridian around it, and consider the eigenvalues of the image of that meridian under the representation rho. I'll call that the holonomy of xi. So pick some. So the eigenvalues are lambda I plus or minus 1 because it's SL2C, so the eigenvalues come in pairs. And you need to choose rth roots of those. This is well defined because the meridians will have different images because this is a non-abelian representation in general, but the conjugacy class they're always conjugate, so the eigenvalues are the same. All right, so again, we have our link, we pick an integer and pick rth roots of our eigenvalues, and from that you can construct something called the rth BGPR invariant. It's a complex number I'm going to denote f sub r, l, rho, mu i, because we need the data, the link, the representation, and the roots. And it's only defined up to an r squared root of 1. So there's some indeterminacy. It's not only invariant of L, but it's invariant under gauge transformations, i.e. global conjugation of rho. So if you move around your base point or like change basis in SL2C or C2, whatever you want to do, it's still well defined. All right. One warning I didn't say above is that actually lambda I can't be plus minus 1 for technical reasons. It's that case is more complicated because some things vanish. I think there's a way to fix this. I'm working on it. Hopefully there'll be a paper soon. But it should be possible. It's not quite there yet. All right. So let's talk about what this means in the simplest case. So in general, we really care about this for like representations with non-abelian image, but let's talk about abelian ones first. Especially because it's really obvious how to construct these representations. So for any link, just pick some complex number that isn't 0. And there's a representation sending every meridian of the link to this matrix TT inverse. So like just basically a scalar matrix in SL2C. And if you have anything with abelian image is always conjugate to that, right? Because you can diagonalize it. If it doesn't have plus minus 1 as eigenvalues, it has distinct ones, so it's diagonalizable, and you can conjugate to one of this type. Except maybe you have different TIs for each component, so you don't have to pick the same T for every component of your link. In that case, this is actually something that's already known. So then this like abelian case of the BGPR invariant is actually called the Akutsu Deguchi Otsuki invariant, or the ADO invariant. These are family invariants due to those three authors that are some kind of generalization of the Conway potential, aka the Reidemeister torsion, aka the Alexander polynomial. I mean, they're not literally equal, but those are essentially equivalent objects. And specifically, like R equals 2 is the Conway potential, and the remaining ADO invariants are some kind of generalization of that. Okay, so that's the simplest case, the abelian case. The novelty in this construction is that you can do it when rho doesn't have abelian image. So in that sense, what f sub r is, it's some kind of non-abelian deformation of the ADO invariant discussed previously. Maybe that's not very informative. To some extent, this has only been defined, so we're still trying to understand better what it really means, but that's the basic idea. And the idea is that instead of these variables ti in the diagonal, those correspond to my eigenvalues lambda I. That's why I choose like rth roots of the eigenvalues. And again, the novelty in this construction is that we can use non-abelian row, so it's some kind of more general invariant. Actually, if you pick r equals 2, you can explicitly say what we mean by a deformation. So there's an actual theorem there that's due to me. We'll get to that at the end of this talk. Actually, sorry. I'll explain how to prove it at the end of this talk. I'm going to say what it is in a second. Here's something related to that. So another thing in this sort of abelian, non-abelian link correspondence, link invariant correspondence. So you remember that the Reidemeister torsion of a link, really of the link complement, is a topological invariant that's constructed using, well, one of the ways of constructing it is using the row-twisted homology of the link complement with coefficients in row. And if rho is sufficiently non-trivial, so in particular if it satisfies some similar no eigenvalues are 1, plus minus 1, or no eigenvalues are 1 condition, then the homology is a cyclic, which seems boring, but actually it's good because it means we can get this numerical invariant out of it called the torsion, which I'm going to denote tau of L rho. For abelian representations, the simplest possible one is an abelian representation, a representation with a abelian image, where you just send every meridian to some variable t. This is basically the abelianization map. And then your invariant is going to be a Laurent polynomial in T, which is the Alexander polynomial. That's one way of constructing it. You could do something similar with this abelian representation T inverse, and you're going to get the square of the Alexander polynomial. The reason that it's a square is that there's two factors, so each one gives you an Alexander polynomial, and and then it winds up being symmetric in T and T inverse, which is nice. All right. If you do this with a non-abelian representation, you're going to get a twisted or non-abelian Reidemeister torsion, which just means it's a generalization where you don't use a simple representation, you use a more complicated one. All right, so what I proved recently, the paper is just on the archive, is that if you have a link in S3 and a representation that never has 1 as an eigenvalue for any meridian of x, any meridian x of your link, then this multiplication where you take f2 times like f2 of the opposite link is equal to the torsion. So here, again, by L bar, I mean the mirror image of L. You sort of reverse all the crossings. And you have to change row a little bit too. It's just sort of the obvious representation of the oppositely oriented link complement. Here's one way of thinking about what that means. If you compute the torsion using this abelian representation, x goes to T inverse, it's going to factor into two pieces because the matrix has two blocks. Yeah? And each piece is equal to the Conway potential of the link. For a non-abelian representation, it's not really obvious how to factor into two pieces, right? It's not diagonalizable because you have non-commuting matrices, but that's exactly what the BG PR invariant does. So therefore, you could call F2 of L rho like a non-abelian or twisted Conway potential. It's some kind of generalization of the Conway potential where you are not using the abelian representation anymore. Okay. The reason this is significant is that torsions are useful. They were used to classify lens spaces, even in the abelian case. The Alexander polynomial is very useful. In particular, twisted Alexander polynomials, which are closely related to this twisted Reidemeister torsion, are very useful in knot theory. There's lots of interesting results about using them to distinguish knots and detecting fiberness and things like this. And so my hope is that this result says that these quantum Holonomy invariants will also be useful for similar things. In particular, one very interesting result is that there is a theorem that you can compute the hyperbolic volume of a knot complement using the hyperbolic structure, the torsion twisted by the hyperbolic structure, in some kind of asymptotic limit, a lot like the volume conjecture limits. And the hope that if you figure out some kind of relationship between f sub r and these sorts of torsions, maybe you can take advantage of this result and say something about volume conjecture type limits of quantum invariants. All right, so that's what it is. Here's how to actually construct the BG pair invariant. This is probably the most technical part of the talks, so I encourage you to watch it no matter what, but if you haven't seen quantum groups before, this might be moving a little fast. Okay, so we're going to use quantum SL2 to do it. It's an algebra over rational functions in Q, generated by k to the plus minus 1 e and f with these relations. So k sort of Q commutes with e and f, and then e and f have this sort of weird k minus k inverse thing. What you should think of this as usual, is that it's really a Q analog of the universal enveloping algebra of SL2. So, right, U of SL2 is this fairly well understood algebra. This is a Q analog of it. As you take Q to 1, these relations go to this of SL2. You should think of k as being Q to the h, so it's like a multiplicative version of the usual Cartan element. The center of UQ is generated by the quantum Casimir, which is a lot like the regular Casimir, which has some expression. We won't actually know what it is. Here's some useful properties. Oh, sorry. So this is fairly well understood. It's what gives you the Jones polynomial. If you've seen quantum groups, you may know that some weird stuff happens when you pick Q a root of unity. When Q is not a root of unity, it's fairly simple. Everything works a lot like regular SL2. At roots of unity, things go weird. So I'm going to pick a 2rth root of 1. You actually can do this for odd roots. I'm going to stick to even ones for simplicity, but both cases are treated in this BGPR paper. All right, so here's some properties. All of a sudden, uc so I should have said that. I'm going to call, instead of calling it q, I'm going to call it c because I want it to indicate that it really is a root of unity, not q anymore. So at a root of unity, uc is rank r squared over the central subalgebra z naught, which is just generated by all the generators raised to the rth power. You might expect that because you can see here that if these are both to the rth power, if one of these is to the rth power, you're going to get q to the 2r, which is 1. Similarly here. And this relation is less obvious that things become central, but you can do some q analog stuff and it works out. All right, so I have this big central subalgebra, which, as I mentioned at the end of the last part, is very important, is a good thing if you want to get quantum invariance. So Z naught is commutative, which means that it's a commutative Hopf algebra, so it's the algebra of functions on a group. Specifically, the spectrum of Z naught is SL2C star. I'll say what I mean by star in a second. It's not the dual group in the usual sense. Finally, the center of UXI is basically just Z naught. There's also, it's just Z naught and the Casimir, which is subject to an R3 polynomial relation, something with Chebyshev polynomials. I will explain what I mean by SL2C star instead of SL2C. It's the Poisson dual group of SL2C. We'll get to that later. All right, so here's how to get the grading on the representations of this that we need for like a G-graded version of the RT construction, which is how we're going to get our quantum holonomy invariance. So closed points of the spectrum of Z naught are just characters of Z naught, by which I mean algebra homomorphisms from Z naught to C. And specifically, these are going to parameterize points of SL2C. So if I have some matrix in SL2C, which I'm using this maybe slightly weird looking coordinate system, but here kappa is some non-zero complex number, epsilon and phi are any complex numbers, I can associate this matrix to the character that sends k to the r to kappa, chi b to the r to epsilon with some factor, chi of f to the r to phi over kappa with some factor. And a representation V of uxc with SL2 grading chi, so SL2C grading this matrix, is just one where Z naught acts by this character. It has represented this character chi. So if you're familiar with quantum groups at roots of unity, you might know that the representation theory gets weird. It's not semi-simple, and there's some complicated tensor product rules, and things are more complicated. Actually, when we stay away from the identity, so when this matrix is not the identity matrix, it doesn't have one, in particular, it doesn't have plus minus 1 as an eigenvalue, things are much nicer. That's why we had this restriction about plus minus 1 not being allowed earlier. In particular, here's this theorem. So if you don't have plus minus 1 as an eigenvalue, then every representation with character chi is projective, irreducible, and r-dimensional. So you don't have any smaller ones, they're sort of all pretty similar, and there are isomorphism classes of them, and all you need to do is tell me how the Casimir acts on them, and it tells you which isomorphism class it is. So that's very nice. The representation theory is pretty well behaved in this case. And the idea is what we're going to do is we're going to strand a strand with holonomy chi to a representation with character chi. But there's r of them, right? So we need to pick which one we want, and that's what this extra data of the roots is. There are irreps, there's some kind of r-degree polynomial relation describing them, so you just like pick an rth root of it, and it tells you which one you're picking. There's an automorphism r check from uc, tensor uc to itself, satisfying the Braid relations. By that I mean it satisfies some kind of Yang-Baxter equation, so the induced thing will wind up satisfying the Braid relations we want. If uc were quasi-triangular, then r check would be conjugation by the universal R matrix, followed by swapping the tensor factors. For technical reasons, that isn't really true. Also, the swapping the tensor factors is why I'm calling it R check instead of R. So this is related to the fact that Q isn't technically quasi-triangular either. Actually, the one that is UH, the H-adic version. Remember that Q is e to the H. And so even though UQ isn't quasi-triangular, UH is, the R matrix for UH still works in UQ because sort of it acts nilpotent on modules, so things converge. But for UC, at a root of unity, it no longer converges. So it doesn't really make sense to talk about the R matrix for UC, but what you can talk about is this conjugation action. That is well-defined, but it's an outer automorphism. Okay. However, this outer automorphism acts non-trivially on the center, on Z naught, tensor Z naught, which is what these characters are functions out of that, and the characters will give us the grading. So what we get is this map of modules, so here this means module with character chi1, i.e. group element chi1, chi2, and notice that they change across this transformation. So the isomorphism classes have changed, and also notice that I've written chi3 and chi4, not some kind of conjugation action. So the change that happens here is not conjugation, it's something more complicated. Okay, so there are some problems with this that are fixable, but some problems. One of those is that the action of modules is only defined up to a scalar. So you can, because it's an outer automorphism, not an inner one, basically, you can fix this, but then you get this root of unity indeterminacy. So that's where that comes from. All right. A more serious problem is that this map that I showed you before, chi1, chi2, between the chi4, chi3, between the characters, is not the conjugation action on SL2C. It's some more complicated thing. So this is fixable. It's related to the fact that the spec of Z naught is not really SL2C, it's SL2C star. In particular, the group structure is different. It's this sort of weird subgroup of GL2 across itself where you sort of split things into upper and lower triangular parts. What it is it's the Poisson dual group, which is because this is a Poisson-Lie group, so it has a Poisson-Lie bialgebra, and you can take the dual of that structure, and this is the associated group. This Poisson dual business is a general feature of quantum groups at roots of unity, that the central subalgebra is the ring of functions on the Poisson dual group to the original thing. SL2C star is not SL2C, and doesn't have the same group structure, but it is birationally equivalent. Right? This map is almost an isomorphism. It sort of misses a small closed set, but it's not a group homomorphism, which is why it's okay that this is not actually the conjugation action, because sort of it's in a different group, so it shouldn't be. However, this is fixable by some kind of theory of factorized biquandals. So to say what I mean by that, I need to say what a quandle is. So this braid group action on the colors before that we previously mentioned is something called a quandle. Specifically, it's the conjugation quandle of SL2C. A quandle is an algebraic structure that basically describes colors and arcs of knot diagrams. So conjugation is an example of that kind of thing, right? And when you do a braid, you have to change the colors in a certain way, but there are more general quandles than just conjugation. They come up in knot theory all the time. This action of our check on the characters that gives you this action SL2C colors is not a quandle. It's actually a more general thing called a biquandle, because kind of both halves change. But this biquandle is related to the original conjugation quandle of SL2C that we want. It's a factorization. So one of the things that's done in this BGPRI paper is it works out this theory in detail. So if you don't really buy what I'm saying and you want to understand what it really meant, you should read that paper. There's also some issues where I know I said it was birationally equivalent, so this is only a generic equivalence, but you can show that that's fine. All right, so the summary of all that is that we're not actually going to get a representation of this braid groupoid B of SL2C that I was talking about before. We're going to get a different, closely related thing I'm going to call B of SL2C star. So it's like you could call it the biquandal factorization of the conjugation quandle of SL2C, like the associated groupoid, something like that. Okay. The point of all this is that there is a theory that lets you say that you can instead of using closures of this to describe links with SL2C representations on their complements, you can use endomorphisms of this. So you have some different kind of colored braid. If you didn't understand what I was saying, here's one way to think of it. The grading on UC modules is not quite right. It's the wrong group, but it is fixable. You just have to use a weird coordinate system. That's really all this is. And so if you use that sort of non-standard coordinate system, then everything works out. All right, there is one more problem now that we've dealt with this issue with the gradings. Remember that in order to actually get an invariant of links, you need to take their closures, right? You need to take these sort of traces or quantum traces. And there's this problem where, as I mentioned before, UC is not semi-simple, which means that the quantum dimensions of lots of irreps, in particular ones we want to use, are 0. So, like if you sort of take the trace of a map from one of these nice R-dimensional modules to itself, you'll always get 0. In particular, if you just naively go through this construction as we're talking about now, your link invariant will be 0 for all links, which is not a very useful link invariant. Again, this is fixable. Here's an idea of how to fix it. So one thing you can do is take partial traces. So if I have some map on n strands from these modules to itself, you can sort of take the trace on the right n factors, yeah? And when you do that, you sort of get rid of most of the complexity, so you still have some kind of map from VG1 to itself. This is also known as writing your link as a 1-1 tangle. That is just like sort of close everything down to the point where you only have sort of one pair of ends on your strand. One strand with like free ends. All right. When I do this partial trace, it's endomorphism of an irreducible module, right? V1 is irreducible. So by Schur's lemma, I can write this map as some scalar bracket of it times the identity map. I don't have to make any choices to do this, right? I'm just pulling out a scalar from the identity map, which is canonical. When I do that, then if you think about it, the trace of this partial trace, so the trace of the full thing, should just be this scalar times the quantum dimension of V of G1, right? If I have a scalar map on a vector space, the trace of that map is the scalar times the dimension, and that still works for quantum things. So the idea is that instead of tracing all the way down and using the actual zero quantum dimension, we pick some kind of new modified or a normalized quantum dimension, d of V of G1. And if you choose these correctly, you can do it in such a way that this will still be invariant to the closure. Right? The tricky part here is that you need to be careful because there's different modules, right? Like G1 could be a lot of different things. If I conjugate, it'll change which color it is, it'll change. And I need to make sure that I choose my colors in such a way that it's actually consistent. Okay, this can be done. They're called modified traces, and they're useful for stuff like this. This theory is due to Geer, Patureau-Mirand, and a number of other authors, but they are two of the authors of most of these papers. So if you want to look up this stuff, those are the names to look for. Anyway, their theory tells you how to do this. I won't say more about it because it's pretty algebraic. It is interesting, but not in this talk. All right. So in summary, what our algebraic constructions have given us is we have some kind of functor that's some kind of Reshetikhin triad type thing that goes from this braid groupoid that's not quite the braid groupoid associated SL2C, but a factorized version, but something equivalent to it, basically, to representations of our algebra UC. So if you want to compute your link invariant, so write your SL2C link as the closure of a braid in B of SL2C star, and do this business with taking rth roots, which does not complicate it much. And if you take the modified trace of that braid, or if the image of that braid into this functor, you get an invariant of L. All right, so that's how to get it. So I mentioned before that I said that it's related to torsion. I'll talk briefly about how to actually prove that. So remember that my result that I discussed previously is that if you pick r equals 2, the sort of simplest case, and you take f2 of L times f2 of L bar, you get the torsion. So you could call this like the norm square because this is something like f times f bar. It's like the complex conjugate, something like that. It's actually not the complex conjugate in this case, but okay. So the way you prove this is you need to work with this squared representation. So you take the pointwise tensor product of f and f bar, where f bar is like a mirrored version of f. You sort of invert all the gradings, do the opposite multiplication, take the braidings backwards, the usual stuff that happens when you do mirror images. So by pointwise tensor product, I just mean that like it's going to be a map into U tensor U modules, not U modules, and sort of everything is just tensored. You can think of this, if you know what a quantum double is, which is a construction that appears in, for example, the relationship between Reshetikhin triad and triad Viro, aka surgery and state sum invariance. This is like a graded quantum double. One of the novelties of my paper is actually constructing this thing. It hadn't really been written down in this form by anyone as far as I know. Okay, so on the one hand, the definition of f tensor f bar is more complicated than f, right? They're bigger vector spaces, there's more stuff going on, but it's actually easier to work with. Roughly, like, there are some cancellations that happen, and things work out nicer. Some things are invariant that were invariant before. It's just easier to prove stuff about it. You might be familiar that a lot of times it's easier to prove things about triad Viro invariants than Reshetikhin triad invariants. They're kind of better behaved. All right. What this has to do with Reidemeister torsion, like I said, is if you recall that in general, one way to define the torsion is to use this thing called the Bureau representation of the braid groupoid, which basically comes from the braid group action on this row twisted homology I mentioned before. The twisted torsion is defined using a twisted Bureau representation. Not surprising naming, and that's some kind of analog of this for this colored braid groupoid B of SL2C. In my paper, what I basically show is that the supercentralizer of the image of this functor is naturally isomorphic to the twisted Bureau representation. This is a kind of, I even call it a Schur-Weil duality. So remember, Schur-Weil duality says that if you want to understand the tensor decomposition of GLN representations, you show that the centralizers have something to do with symmetric groups, and then you get this correspondence. This is a similar kind of correspondence. Use a double centralizer theorem. Once you have this result, it's not too hard to show the relationship you want with the torsion. Like, you can take some trace, and it's very easy to show that the trace you're taking is the same trace or determinant that you take in the Bureau representation. All right, that's all I had to say for now. Again, I'll remind you, if you have any questions, you should post them at ncngt.org. If you would like to ask me more detailed questions or have a talk about this or any related math, I would love to. I'm sort of stuck at home alone, so send me an email and get in touch. And finally, these slides will be posted online at sl2.com, my website. Thanks.